Okay, I just want to take a few minutes and wrap up the concept of differentiability. Before we were just talking about how can you determine whether something is differentiable or not, meaning can you find the derivative of it. And we said there were two situations where you could not take the derivative. And that was if you had a sharp point. You can't take the derivative at a sharp point. A sharp point being, if these are your axes, your graph goes like this, right? It is continuous at that point. The function is continuous. So the limit of the function exists. However, the limit for the slope doesn't exist because the slope approaching that point from the right and the left are not the same. Okay, so it would be not, you cannot take the derivative at a sharp point. You also cannot take the derivative this would just be an example of a function that's almost vertical but not quite. Because if it was vertical, obviously it wouldn't be a function. But you cannot take the derivative where the slope is undefined. Okay, so those are two situations where you cannot take a derivative. So a couple of quick examples then. Is the absolute value of x differentiable everywhere? Is the absolute value of x differentiable everywhere? And the answer is, if you were to graph the absolute value function, it looks like a V. Right, that would be the absolute value of x. And obviously this is not differentiable at 0 because there's a sharp point there, but it is differentiable everywhere else. So to answer the question, no, it's not differentiable everywhere, but it is differentiable everywhere except at 0. Okay, so that's the idea behind that. A couple other quick examples that are important to note. If you have a function, for example, here's c, and you have this function. You have this function like this. So the rule of thumb is if a function is not continuous, it is not differentiable. You cannot take the derivative. Which should make sense because we don't have anything going on, right? There's no point. Remember, the derivative is the slope of a curve at a point, and there's no point here, so I can't take the derivative. Okay? However, the converse is not necessarily true. Okay, I could have this graph here, which it is continuous, but I have that sharp point, so it's not differentiable. Okay, you can have a graph that's continuous but not differentiable. So the takeaway here is if a function is differentiable, I'm going to abbreviate here, is differentiable, it is continuous. So if you can differentiate the function, it has to be continuous. Okay? It's going to be continuous. But if it's not continuous, it's not going to be differentiable. Okay? So if it's differentiable, it's continuous. But if it's not continuous, it's not differentiable. Now, if a function is continuous, it may or may not be differentiable. But if it's not continuous, it's not differentiable. So that's the difference, okay? If a function is continuous, like this is continuous, but it's not differentiable, right? A sharp point is continuous but not differentiable. This function is continuous and differentiable. So continuity doesn't necessarily imply differentiability, but the opposite is true. If it's differentiable, it has to be continuous. Okay, so those are a couple of quick things I just wanted to go through to kind of wrap up the idea of differentiability. We'll get into some other examples of how to take derivatives as we move on. I do want to do one other example for you of instantaneous velocity, and let's talk about our position vector. We talked about this before, right? Velocity has magnitude and direction, where speed only has magnitude. So if I'm talking about magnitude and direction, I have to have a position to give me that direction, right? I can't talk about directions if I don't have a starting position and an ending position. So we talk about the position function. So in this particular example, our position function is 1250 minus 16t squared. And you're going to do three things here. You're going to find your instantaneous velocity. So find v of t and determine when we hit ground. So I'm going to abbreviate when hit ground. I know that's not grammatically correct. But when we hit the ground and how fast hit ground. So how fast is it going when it hits the ground? I totally understand that this is not grammatically correct. Just in the interest of space and time, I just want to get those out there. So the first thing we're going to do is find our instantaneous velocity. In order to do that, we have to take the limit. Let me just squeeze that in there. The limit as h goes to 0 of s of t plus h minus s of t, all of that over h. Because we don't have a specific value, we're going to just take the limit of this and get that in general terms. So here we go. We have the limit as h goes to 0 of s of t plus h. So that means we would have 1250 minus 16 t plus h squared minus 1250 minus 16 t squared. All of that over h. And that would give me the limit as h goes to 0 of 1250 minus, and again, if I expand that out, I'm going to combine a couple of steps here all together. 16 t squared minus 32 th minus 16h squared. So I combined several steps there. I expanded the t plus h squared, and then I distributed the negative 16. Okay, and then here I'm going to distribute that negative sign, so negative 1250 plus 16 t squared, all of that over h, which gives me the limit as h goes to 0. My 1250s are going to cancel, my 16 t squares are going to cancel, so I'm left with negative 32 th minus 16h squared over h. I can go ahead and factor an h out of this, because remember right now I cannot find the limit because my denominator would be 0. So I'm going to go ahead and get rid of that h in the denominator by factoring the h out of the numerator. So that leaves me with the limit as h goes to 0 of negative 32t minus 16h. As h goes to 0, I end up with negative 32t as my instantaneous velocity. Okay, so that is my instantaneous velocity. Okay, my instantaneous velocity is the first derivative, so that would also be the same as s prime of t. Okay. The second part, I'm just going to go on to a new screen here. The second part is at what time or when does it hit the ground? Okay, so this is part 2. When does it hit the ground? Remember, my function was s of t is equal to 1250 minus 16t squared. I hit the ground, right? When I hit the ground, my position is at 0, so all I'm going to do is solve this. 1250 minus 16t squared is equal to 0. And I solve that, I get negative 16t squared is equal to negative 1250. So t squared is equal to 78.125, right? And then I just take the square root of that. If I round that, it's approximately plus or minus 8.84 seconds. Obviously, I can't have negative time, so my answer here is going to be 8.84 seconds. So at 8.84 seconds after something is falling, right, I would hit the ground, right? So it says when does it hit the ground. It didn't really give you much of a precursor to it about what's going on. You're talking about dropping something off of a really high height, actually a height of 1,250 feet. That's what this equation is saying. I want to know how long does it take for it to hit the ground. It hits the ground after 8.84 seconds. And now I want to know how fast is it going when it hits the ground. So in that instant that it hits, how fast is it going? So I'm looking for that instantaneous velocity. That was what we found in the first part, was negative 32t. And I'm going to go ahead and plug that in. And that gives me negative 282.88 feet per second. And that negative doesn't mean that it's traveling at a negative speed. Remember, velocity talks about magnitude and direction. That just means it's going down at 2.88 feet per second. Okay, so it's hitting the ground at 2.82 or 282.88 feet per second. That's the instantaneous velocity as it hits the ground. Okay, so that would be an example of a type of a word problem that would go with instantaneous velocity in these types of problems. Okay, so that pretty much wraps up the idea of instantaneous velocity and some concepts having to do with differentiability. Take care.